Hi everybody. Today we're going to be starting chapter 12 in the book. Its title is Parametric and Polar Curves. I think this is really exciting because it gives you an entirely different way to sort of think about the kinds of curves that we use to model physical phenomena. I thought I'd first introduce this by showing you a mode on your calculator you probably haven't played with before. So let's bring the calculator to a place of prominence, and actually maybe I'll zoom in a little bit on it too. So yeah, the mode button has a couple of options that you've probably used before, like normal versus scientific versus engineering style notation for numbers, whether we want to go to floating point or have a certain number of decimals as a set accuracy. This is one you've used before, radians versus degrees, right? You can switch back and forth between them. I'm going to leave us in radians, but I doubt if people have messed with this next setting before. This is almost always left in the func or functions position. Let's switch it now to par. And what that's going to do for you is, just quit out of there. When you hit y equals, you will no longer have y equals. You have x equals and y equals. And so you get to specify both the x and the y coordinate of a point using functions. And the functions are functions of something we call the parameter. Usually they call it t in the calculator, but it can be other variables. T is meant to make you think about time, and time is quite often the parameter you're thinking of. So imagine you've got an Etch-a-Sketch now, right? You've got one knob that controls the x and another knob that controls the y, and that's what those things are. Let me give you a quick example. Suppose I stick in the cosine function, and by the way, when you hit the button to get the x variable now, it comes up as t. So that's one change that happens when you're in the parametric form. If x is cos of t and y is sine of t, what curve are we going to get when the x coordinate is the cosine of a parameter? Now you might think of t as being a theta, an angle, and y is the sine of that angle. You should probably know what you're going to... Oh, wow. Terrible window, isn't it? Let me put the zoom back to... Don't hit second. Let me put the zoom to, what's the standard one, 6. And then we get a very, very tiny circle. Darn. It's also kind of flattened. Do you notice that? This is just a matter of the aspect ratio. This screen is about 1.5 inches wide, but it's a little over 2 inches. Keep saying things backwards. 1.5 inches tall, a little over 2 inches wide. So things that are square don't look right. There's a zoom level on here that's meant to fix that. Have you ever noticed z square? So let's hit that one this time. And now we've got an even tinier thing, but it does look more circular. All right, how about if we zoom in on that? At last, something that roughly looks like a circle. Awesome. You can play with the graphing calculator now to draw all kinds of things parametrically. For instance, well, no, there's. Let me go back to a slightly better technology so that we can play with the for instances there. The better technology I have in mind is Desmos. So I've already pulled up a Desmos plot, and I'm doing some wild Desmos things here for you. Probably want to zoom a little closer so you can see it bigger. This is a parametric plot in Desmos. Basically, you specify... For some reason, I've got extraneous parentheses here, which I'd like to kill off. Nope, that last one I didn't need. But what I'm doing here is plotting something where, well, I specify it as a point, right? I've got a function in the x-coordinate and a function in the y-coordinate. Now, ordinarily, you specify a range of values here, but I got tricky and specified them in terms of a parameter themselves. Wow, this is a lot to do. Let's start fresh. I'll just draw a circle for now. If we make a plot that has cos of t in the x-coordinate and sine of t in the y-coordinate, notice how it automatically realized I didn't want a slider for that, but just created a range of values. And the appropriate range for t, if we're going to be talking about drawing a circle, is 0 to 2 pi. Let's put it in as 6.28. Yeah, close enough. So that's how you draw a circle. Now, the problem is that you see the circle sort of already finished, and I really do like to see the circle changing with time. I watch it being drawn in, which is sort of fun. You get to see how the parameters changing affects the amount of the curve you've drawn so far. So I'm going to make the upper limit of this a, and we will add a slider for a. Now, I don't like the default settings for that, but I'll start a at 0 and end it at 2 pi, and we'll leave the step alone. The Desmos can decide what to use as the step with that range. All right. So when a is 0, we don't see any graph. As we slowly move a up, you see it draws more and more of the circle, which is fun. Now what I'd like to do is play with some of these functions, right? Maybe, well, suppose I kept the cos the same, cos of t, so the x-coordinate will still be wagging back and forth across the circle we're doing here. But what if we went around and changed the sign so that it went through the cycle twice while we're doing it? That is a change of scale in the y direction. No, it's not a scale. It's a frequency change in the y direction. Oh, I get a infinity sign. If I go up to 3 of them, I get that. If I go up to 7 of them, I get this. What's I find really fun to do is to have this graph it just over a slight range. Say, a is the upper limit and a minus 8.3 as the lower limit, and then play it. You get to watch the thing. You know, we're only drawing a portion of the graph. Actually, what's probably really fun to do is to make another copy of this thing. And here we'll draw the whole thing. So from 0 to 6.28. I'm going to move the y coordinate down just a little bit so that we see both of these things at once. And the other thing I probably ought to do is zoom in enough that we can really, see what's going on better. Maybe we'll even, I can't entirely hide the expression list. First I've got to hit go on the plotting, then I'll hide the expression list. And you can watch the thing. I'm just having a lot of fun with this. The kind of plot that I'm showing you actually has a name. This is called a Lissajous figure. And Lissajous was a French electrical engineer who realized that he could power an oscilloscope and apply different frequency voltages to the things that control the X and the Y, and he made these lovely designs. And people, well, when I was a kid, almost every crazy sci-fi movie had a picture of an oscilloscope with one of these Lissajous figures in the background. Okay, so what else can we do with the notion of a parametric curve? Let's get boring before we go into more excitement. What about if I just wanted to draw a line? When we've got a line drawn in the ordinary y equals f of x form, you use mx plus b and it's nailed down. But what if I wanted to have a parametric line? Then I'm going to want linear functions in both the x and the y slots. But an easy trick is to put the x-coordinate just to be the parameter, and the y-coordinate to be, well, m times that parameter, which is x, plus b. And yeah, let's add sliders for them. So here I've got a line. It's only drawn for the parameter value from 0 to 1, and I guess I should change that, huh? How about if we go from -5 to +5 on this line? There it goes. You see a line that covers the whole, well, not the whole graph, right? It goes all the way back to x is -5 and up to x is +5. But basically it looks like a line, and if we can change the slope and we can change the y. You can get parametric lines though in other ways. This is sort of a cheap stud. For instance, if I added 1 to the x coordinates, that's going to move the line sideways. And if I, at the same time, added 1 to this x coordinate, you'll notice that we're back into the same mx plus b form we were at. You see how I've got a slope of 2 and a b of 3. Here's a b of 1 and a slope of 1. But you see the two functions that I've got are no longer really x and mx plus b. They're x plus 1 and mx plus m plus b. The point I'm trying to make there is that you can substitute any linear equations into each of the slots, and you'll get a thing that looks like a line. Don't take my word for it. Let's just do it. How about if we do 3 times t minus 1 in the x coordinate and 2 times t plus 2. Now, the m and the b, I don't need them anymore. I put actual values in for that. Now, how could we figure out the slope of this line? I'd kind of like to know what's the regular functional form for it. It somehow must depend on these parameters I put in. I've got a 2 times t in the x coordinate, in the y coordinate, and a 3 times t in the x coordinate. Well, let me point out something that it doesn't depend on. If I change the linear part, that is the constant part of that equation, actually, here, let's put a variable in there and it'll make a slider for us. If I change the constant part of that thing in the x coordinate, it doesn't have an effect on this slope. The slope is staying the same. Similarly, I can make the constant part of the y variable be something that we can change, and that doesn't affect the slope either. Okay? So it must just be the numbers, the 3 and the 2, the individual slopes for the x and the y coordinates that determine the slope of this thing. Well, maybe can we actually see what the slope of this thing is? Let me put it in a convenient place so that we'll be able to measure along the curve. Trying to set it up so that it passes through the origin. Doesn't want to quite hit there, but close enough. You can see the nearest place where it also goes through an integer point, or very nearly goes through an integer point, because I can't set the slider perfectly, is here at 4, 6. Actually 6, 4, isn't it? 6 in the x coordinate, 4 in the y. And so we have gone over 6 units and up 4 units, or a slope of 4 over 6, 2/3. Now the numbers here were 2 and 3. It's certainly not a coincidence. So here again, I think it might be nice for us to sort of watch the line being drawn, rather than just have it drawn and that be static. So well, actually, we can copy and paste this formula right into there, and we'll make the upper limit be, I need a new constant. How about C? It's our next one. We'll add a slider for that in a second. I'm going to have C minus 5. Here's our slider for C. Okay, so The other thing I'm going to want to do is separate these two things just a little bit so we can tell the difference between the part that's being drawn. Another thing that might be smart is to change its color. How about we make this guy be orange? That'll be really ugly next to the purple. And I'm also going to lift it in the air just a little bit. Well, that may be a little too much. About 0.1. There we are. So you can now run C from -10 to +10 and watch the curve being drawn. -10 to +10 might be a little much. How about -5 to +5? Yep. Let's play the curve. Oh, it's going back and forth. I hate that. And then back the other way. Yeah, that's too much. Let's make them go both ways in the same direction. And also, it looks like the range I chose is still a little too large, so maybe we can change these numbers then. -2 to 2. Now go. I went a little short on the high end, so how about we go? Let me pause that a second. How about from -1 to 3? See how that looks. There you go. Our orange line segment is drawing across the thing. Now, why is it that that guy is producing a slope of 2/3? Well, think about how at any one moment in time, the x coordinate is changing. That is this function 3 times t minus a. It's changing relative to time. I mean, that is a function of time. It's its derivative, and that guy's derivative is 3. So the x coordinate is changing 3 times a little change in x. This length of the orange line there is supposed to make you think about that being a delta t, right? And the y coordinate is changing as the derivative of the y function with respect to time, which is 2. So the height of this little orange dash is 2 times delta t. The width of it is 3 times delta t. That makes the slope, the ratio of those two things. The y's change over the x change, 2 to 3. Kind of cool. So I could arrange to have a different slope if I wanted. One thing that's really fun is I can easily now make infinity slopes. How would I make an infinite slope in this form? I'll make the x coordinate not depend on time at all, just be a constant. And that just means got to make the same change over here. It's just this value a, which, put it over that way. Oh, darn. Now I want to actually do the little offset in the x direction, because otherwise too much. Oh, I see. I times. I'm going to say plus 0.1. All right. So now again we can play the animation and see the little line segment drawing along at least right next to the vertical line. Think about how you would make a change to make the line be horizontal. Yeah, just make the y coordinate not depend on t. Yeah, so lots of fun. You can use parametric thinking to draw all kinds of stuff. What about if you wanted to draw one of your old familiar curves, like, a parabola? Let's do that next. Do I want to keep any of these sliders and things? They may be fun, but we may have to mess around with the values of them. I don't need the A and the B, though, but I'm kind of wanting this. I'm kind of wanting this slider for C that's... So what if I want to get y equals x squared? First, let's draw that sucker. Y equals x to the second. That's the usual graph of it. But I want to do this with a parametric form. It is quite distracting having that slider running around in front of you. So C will be the parameter. Now let's just draw it root. I'm going to make a point, and the x-coordinate of that point will simply be the parameter t, and the y-coordinate of the point will be the same function of the x-coordinate that we were trying to draw. So this would be just t to the second power. And we've solved the part of it from 0 to 1. I can run the parameter from minus 3 to 3, like that. And I can also play the same trick I just did a minute ago to draw a little piece of it and sort of watch it in motion while you draw it. But I think you get the idea. The time value of minus 3 corresponds to this point, and the time value of plus 3 corresponds to that point. You can actually just, rather than this line segment stuff, you can get Desmos to draw a point in motion, but right? I think I can. Now I gotta try. A comma a to the second. We're gonna add just a little, so no, the point should be fine. We'll add a slider for a there. Yeah, so you get a point that can be put in motion. Darn it. I accidentally middle clicked on something. Yeah. Okay, so if we want to see the point moving along the same thing, let's put it from minus 3 to 3, and I'll leave the step alone. And you can play a movie of that portion of the parabola being drawn by the point. Now there's this actually points out something else that we can do. Do you notice how the point seems to slow down there at the bottom and go rather fast up at the top edges of the thing? Why is that? Well, again, it's because its speed is related to the derivatives of the x and the y coordinate things. You can manage to make the same exact curve by changing effectively what a is. You could think of it this way. You could draw quickly at first and then slow down as you got to the other end, right? So I could make the a here be a function of yet another parameter. I'm talking about composing things, but let's just do that in the inside here. How about if I take how about the square root of a? Now clearly I'm going to have to make the a run only in positive values if I'm going to take square roots. And then a itself. I could say the square root of a squared, but that's probably not what you want. And before we get into trouble and the Desmos blows up, we'll run it from 0 up to, say, 4. Right? I think that's going to give us an error because there's an extra power thing in there. Okay, so now I can make this point draw along the parabola, but notice how the speeds change. It's going. It's not going as far as I was expecting. How far did I take a out to? I would say it looks like it's going at the same speed over the whole range here, but I think that's partly because we're not quite going far enough. I want to get to the same spot I got to before, so 0 to 9 would be a better. Does it look like that thing's drawing at a constant speed? That's really interesting. I wonder why. If I did want to make it draw at a changing speed, I could replace what I did here with some other function. How about, for instance, how about e to the a? And now the y coordinate has to be the square of e to the a. I feel like the parentheses didn't work out for me that time. Right. Oh, I see how it went wrong. E to the A, get out of there, make a parentheses, then put it to the second power. E to the A to the, honestly, I could have just said E to the twice A, but when A is 0, E to the A is 1, and and 1 squared is also 1, so that's when the top parameter is 0, we're at this point 1, 1. I guess I'm safe now to have negative parameters. Where will we be when A is like negative 9? Wait a minute. At negative 9, I just came down to here and stopped for a second, it looked like. At this end of the graph, this value of the parameter, I'm just sitting at the vertex. And at first, I don't move. Look at that. You just stay and put, and then you begin to move, and then you go really fast. In fact, where is that upper limit? Looks like it's around 1.2, so let's just change the upper limit to that. Okay, maybe 1.1. Better. But why at the low end, at the negative 9, do I get just hanging out near the origin? And then whoosh, taking off. And then, because I'm doing that back and forth thing on the animation, let's do it again in both directions. Both in the same direction. Yeah, well, it has to do with the function that I pre-composed here. E to the A, when A is negative, gets closer and closer to 0. So this parameterization is never going to draw anything in the left-hand branch of the parabola. It's only going to give us positive stuff. The smallest the x-coordinate ever gets is, well, close to 0. You could put other things in here that would change that. For instance, well, I don't know, you could put the x cubed in there. And then you'll have both positive and negative values. Shoot, I mentioned it. We might as well do it. Instead of e to the a, I'm going to have a to the third, and then inside the parentheses here, I'm going to have a to the third, and kind of watch how the changing parameter. Actually, I think we're going to want the parameters to be much different than that. Say from about -2 to +2 would be good. See how that looks. Oh, that's awesome, isn't it? We come zooming in on the left branch, hit the vertex, pause for a little while, and then take off again. Why is it doing that? Well, it's because near 0, x cubed is got a horizontal asymptote, right? So when the parameter is around 0, the inner function here, the a cubed thing, isn't changing very much. So we kind of stay put on the parabola. It's really, I think, amusing to try different things like this to see if we can figure out how to draw the same curve but with different parameterizations, so that we can model physical phenomena. I think I'm going to stop with one last example of this kind of nonsense. Let's draw a straight line, but not parameterized so that we move down it in a smooth way. Let's try it. Let's just start from fresh on this. I want to draw a straight line with slope 1, so I'll give it x plus 1 is the x coordinate, and sorry, I better use t, I think, minus that it's a parameter, and then t plus 2 in the y coordinate, and we'll let t go from -5 to 5 so we see a good bit of the graph. Okay. Now, maybe a little farther, in fact, because I kind of like to see the graph filling the window. So how about -10 to 10? Now I'm going to plot a point that has that same parameterization first. So the point will be, let's call it a plus 1, comma, a plus 2, and we'll add a slider for a. And so we can move our point along the curve, right? And if I just play this movie of it moving along the curve from minus 10 to 10, it's just going to move at a constant speed back and forth. But let's try to mess with it some. For instance, what would the effect of replacing a with a squared be? Well, I really can't type a to the second there and a to the second there. It's going to be the same line. I've just replaced the parameter with a function of a parameter. So the way the parameter behaves is different, but what happens to the line that point is on isn't. If we play this one, much different way of drawing it. And there's a portion of the line we never draw. We never draw things that correspond to the original parameter going negative because we've got a squared in there. And we kind of, you notice how when it does poke in from the right there, it comes down and it stops for a second and then it takes off again. A nice way to visualize this might be to change the lower limit on that from 0 to, we can keep it at 10. Actually, 10 is just going off the screen, so that'll be all right. Where are we when a is 0? Notice that that's predictable from the form of the thing. When a is 0, t is 0, we're at 1, 2. The x coordinate is 1, the y coordinate is 2. So those things actually, they tell us something. They tell you the y-intercepts, the b parts for both of those linear curves, linear functions that are going in to give us the x and y coordinates. They tell you the location of when the parameter is 0, where will you be? There's sort of a starting point, right? And because I've used a squared here, I get I can never move into the places that would correspond to negative time because I've used a squared. If I wanted to see negative time, we can do that. Do a different function in here. Change it to a cubed, for instance. With an odd function in there, you'll have both positive and negative values. Let's go from minus 2 to 2 on that parameter. And that's an interesting way to draw the curve. Where this line is, I'm calling it a curve even though it's straight. It's certainly not being drawn in a linear way. We're using cubic equations to draw this line. And there's this neat thing where it kind of pauses in the middle and then takes off again. It goes really fast the farther away you are from the origin. There's lots of enjoyment you can get with playing with parametric curves. But I think that is probably enough for this Desmos toying about. Well, let's get back to doing a little bit more theoretical stuff instead of just toying, playing. So the main thing I want to make sure we hit before I leave this chapter is positive orientation is important, but you can read that and figure it out. They talked about, oh look, the book even did the parametric equations of a line, just like I did. They're nice. They let us know how to figure out the slope from the parametric form, and the point that you will pass through also is visible in the parametric form. That point x naught y naught is the offsets for both the x and y separately, and so those are the coordinates where you will be when t is 0. Neat stuff. But what I wanted to get at is towards the end of this thing, figuring out derivatives. Now, there's a tendency, I think, for people to not like Leibniz's notation for derivatives. That's the dy over dx stuff. But this is a place where it really kind of shines. So let me just point it out to you. You have a function where y is equal to f of t, and x is equal to, say, g of t. And that figures. The book did it in the other order. Let's stick with what the book is doing here. So x is the f of t, and y is the g of t. Now, in Leibniz's notation, I would talk about things like f prime of t. That's what he would call dx dt, right? Derivative with respect to time. And what would g prime be in the Leibniz notation? That would be, g was controlling y, so that would be dy dt. So suppose you had these two fractions, and forget that that's notation for derivatives, just think of them as fractions. And you want to find dy dx. Yeah, well, if you had dy over dt on the top and dx over dt in the bottom, the over dt's from top and bottom would cancel out, yeah, and you would get literally dy over dx. The fact that these differentials follow the same algebra as ordinary numbers is why that notation is so useful. So, but what I had written up here, dy over dt, that was g prime. And what I had written in the bottom, dx over dt, that was f prime. Did I end up writing the same thing as they did in the book? Sure enough, yeah. I can't really highlight, but it's right there. G prime over f prime. So you can figure out the slope along a parametric curve anywhere you like. The other thing that I think is interesting for us to talk about is arc length along a parametric curve. And there's an awfully long description of arc length in here. I would prefer us to go back. One of the first things we did in this course was talking about integration, that there were differential quantities, and when we integrated a differential quantity, we got a palpable version of that thing. If you want to find work, figure out what differential work is and integrate it. If you want to find arc length, figure out what differential arc length is and integrate it. So I want you to imagine we're on one of these parametrically defined curves. So we've got a point in motion, so its x-coordinate is f of t, and its y-coordinate is g of t. And then we let time advance a little bit. So we're at a particular time here, and we go down a little ways from it, and we get a new point whose coordinates are f of t plus, let's call it delta t, and g of, I'm off the screen, sorry, g of t plus delta t. Yeah. Well, how far apart are those 2 points? Right? That's a differential. That's a length of of line segment that I guess I wouldn't call it the differential yet. I would call it the delta of our arc length. A lot of times people use s as a variable to indicate length along a curve. So that's delta s. That's a change in your position or your change in your length along the curve. Right. So how long is delta s? Well, let's kind of blow that region up a little bit, and maybe at the same time think about going down to the Leibnizian limit. We're going to have a small change in t. Let's call that dt. Right? And what that little change in time is going to cause the x-coordinate to change a little bit. The way that x-coordinate, just going to refer back, yeah, the x-coordinate was given by f of t. So the length of this change in the x-coordinate is f prime at t times dt. You may not believe this version of things because I've done some trickery. I took dx dt equals f prime, which is what we called it, right? And I multiplied both sides by dt to isolate dx. Right? So dx is literally f prime t dt, as I've written there. Similarly, what's the other side of this thing? That's going to be g prime of t times dt. And the thing we're after is the hypotenuse here. So Pythagorean theorem, right? Let's think about it. We should have the square root of the sum of the squares of those things. So that's f prime of t dt squared plus g prime of t, off the page, sorry, dt squared. That's our dx. That's the hypotenuse of this differential triangle I'm trying to analyze. All right, so that's f prime squared times dt squared plus g prime squared times dt squared. There's a dt squared in both of those, which we can factor out, and we can even pull it outside of the radical. So ds is equal to radical. This is f prime of t squared plus g prime of t, oops, squared, and the dt on the outside. That looks rather like what we had before for arc length along the curve. We were just getting the version of it where the x-coordinate is just equal to t, and so f prime was 1. Yeah. And then g prime was the function. So that was just the derivative of the function squared. Remember when we had that before? ds equals 1 plus f prime squared under the radical times dt. It's the same thing as this, just a special case of this. So actually we've got a more general formula there. Does the book get around to doing that same calculation? Well, they're being a little more careful talking about deltas and stuff, and instead of jumping to the limiting scenario the way I did. But here's the formula we want. Do you see the thing that's being integrated in order to get length? That's what I would call differential arc length. And integrate that over some region for the parameter, you're going to get arc length. Oh yeah, well, we should do an example, shouldn't we? Why don't I take the example out to the whiteboard now? The classic one we probably got to do first is the circle, right? So a parameterization of the circle is exactly what most of the content of your pre-calculus class, the trigonometry section of the pre-calculus class. Anyway, that's really lopsided. I feel terrible about that. But let's try to get the y-axis more. It's still not very good. But anyway, so the point in motion starts here, and its coordinates are the cosine and the sine of your parameter. And so that's the coordinates, and the parameter runs over the gamut from 0 to 2 pi. Let's see, right over here. T less than or equal to 0, less than or equal to 2 pi. Cool. So the differential arc length on this would be equal to, let's see, it'll be the square root, the derivative of the x-coordinate function, that's derivative of cosine or minus sine, but it's squared, so we'll have sine squared t. That's our f prime squared. The derivative of the y-coordinate, that's, I may be messing up which one is f and which one is y, but it doesn't matter. We'll have this guy's derivative squared and that guy's derivative squared. So that'll be cos squared t. And there's a dt out back. Okay. And you well know that that's just 1. So ds is equal to dt. All right, so what we have to do to get the arc length around this curve, the length is the integral. The parameter goes from 0 to 2 pi, and we got ds is just dt. So integrating dt, you get t, and we'll evaluate between 0 and 2 pi. And this is dull, we're just getting 2 pi. Oh, of course we are, that is the circumference of the circle. So that's correct, but maybe it's not very exciting. So let's try another example. There's a problem in the book that I have my eye on. It's number 85 in the 12.1 exercises. Yeah, so this is the problem I was after. Section 12.1, number 85. The x-coordinate of our point in motion is t to the 4th, and the y-coordinate is t to the 6 over 3. I think I misremembered the problem though. It was 0 to 1 was the, 0 to 1 is the range for the parameter. All right, so I wondered what this looked like. And so I got the Desmos app on my calculator out, and that's what it looks like. It's not really very exciting. You can probably think about this by going, well, what does it look like when t is 0? At t equals 0, you're going to have 0, 0, right? 0 in both slots. So this point is where we start when time is 0. And when time gets to 1, we'll have 1 to the 4th power, which is 1, and 1 to the 6th, that's 1 also, over 3. So 1 unit of time later will be about 1/3 of the units up in the y direction, but 1 unit out in the x. So at t equals 1, 1 comma 1/3. So that's our starting point, that's our ending point, and I guess it makes sense that we move through there like so, in some fashion. Right. In fact, it's real close to a straight line, right? So an estimate for the length that we'll get but here is just the hypotenuse of that right triangle, or the straight line distance between them. That would be 1 squared plus 1/3 squared square root. And that is 10/9, the square root of 10/9. I probably should get out the calculator and find out, but it's just a smidge more than 1, not a very big number. Now what is the process we've learned about finding arc length tell us here? I don't think we need to visualize this. Going from 0, 0 to 1 comma 1/3 shouldn't be so bad. All right, so our arc length element, ds, is going to be the square root of the sum of the squares of the derivatives. Now t to the 4th derivative, that's 4t cubed. So we need 4t cubed squared. And t to the 6th's derivative is 6t to the 5th. 6t to the 5th over 3 is going to become 2t to the 5th. And that will also be squared. And that is all multiplied by dt. Don't know what we can do with this. Let's see. Squaring that gives me 16t to the 6th. Just see what we can do in terms of simplifying. And squaring that gives me 4t to the 10. All right. Both of those, forgot my dt. Both of those have, there's a lot of commonality here. We've got, both of them have at least t to the 6th in them. That one has more. And both of them have at least a 4 in them. So we can pull 4t to the 6th out of those terms. 4 times t to the 6 times, this one has an additional 4 left behind, and this one has a t to the 4th left behind. Great. Now, 4t to the 6th is a perfect square. It is the square of 2t cubed. So I can pull it out of the radical, 2t cubed, and inside the radical we'll have 4 plus t to the 4th. All dt. That's pretty nicely simplified, and that's where we're going to want to start to, well, that's what we're going to want to integrate over the range 0 to 1 to figure out this arc length. I figured I'd save us a little time and copy the integral that we need to do onto the board while I was erasing. Right, so this is the thing we just got as ds a minute ago, and we're going to integrate that from 0 to 1. And it, you know, honestly, this thing was designed to be solved. They were very clever in choosing those functions, because you see this is amenable to a u substitution. Let's check it out. The part under the radical, if you let that be u, then du is going to be 0 plus 4t cubed dt. And we've almost got that. We need an extra 2. We need to make it actually be du there. And so we'll have a 1/2 out front. So our L is 1/2 the integral 0 to 1 of square root of u du. Or u to the 1/2 power. So how does that work again? You add 1 to the exponent, get 3/2, and then divide by that. Don't forget the 1/2 we had out front. And this would be, I guess we can change the limits. U was 4 plus t to the 4th. So when t is 0, u is 4. That's our lower limit. And when u is 1, sorry, when t is 1, 4 plus 1, 5. Right? So those are the right limits for us to work out what L is. So what is it all going to be? Dividing by 3/2 seems foolish to me. We should have times by 2/3. And so we will get 1/3 of 5 to the 3/2 minus 4 to the 3/2. Right, so here I am magically with my calculator in hand, and I just put in the calculation we just said there, and what I got was 1.060. So, you know, pretty close to the guesstimate we had, which was just a little bit bigger than 1. So I think that's going to be a good place for us to stop.